Welcome to the Chemistry channel. Today we are going to look at June 2011 past exam paper, SIMSEC syllabus. And the main topic here is on chemical energetics. So let's start. So the first part of our question, we must state Hess law. State Hess law. Hess law simply states that the total energy change which occurs during a chemical reaction remains the same regardless of the route taken. So for example, let's just illustrate this. We have this chemical reaction A plus B is being converted to X plus Y. So the total energy involved in converting our reactants A and B to the products remains the same regardless of the route which is going to be used. Here the initial and final conditions should remain the same. So basically that is what Hess law is, and we are going to apply it in some calculations. Then the next part of our question, write an equation to define the lattice energy of calcium oxide. We must define using an equation. We mustn't define using words. But in words, lattice energy, this is the energy change which occurs when 1 mole of an ionic compound is formed from the gaseous ions under standard state. And the standard conditions in thermodynamics, for us to say we're operating under standard conditions, we are referring to if there are solutions, we are dealing with 1 mole per dm cubed. The temperature is 298 kelvins and the pressure is 1 atmosphere. So for us to write the lattice energy, so lattice energy of calcium oxide, we must form calcium oxide, an ionic solid, by combining the gaseous ions, which is basically calcium 2 plus gas plus or 2 minus gas. And if this happens, we form CaO solid. So in chemical energetics, it's very essential for you to put the state symbols for you to gain the full marks. Then the third part, construct a Born-Haber cycle for calcium oxide. We must now construct a Born-Haber cycle. The Born-Haber cycle involves the steps involved when an ionic solid is formed. So we always start from the starting point, which I can put as the datum line. And the starting point, you must start with the elements in their elemental state. I'm a bit short, so let me go there. So we are combining calcium. At room temperature and pressure, calcium is a metal, therefore it's a solid due to the strong metallic bonds plus oxygen. And we use half O2. It exists as a diatomic, but it is a gas. So when you combine the elements in their standard states, you form the compound. This is the enthalpy change of formation, delta HF of calcium oxide. So CaO solid. That is what we form when you simply combine the elements. Then the next process, the solid and the gas don't combine directly. So first we must atomize the solid. We must put in energy to break the metallic bonds so that the atoms exist as free atoms in the gaseous state. So, and so this is delta H atomization of calcium. So if you supply this amount of energy, this is what you get. And we've not done anything yet. The oxygen. After atomizing, we now remove the electrons in the outer shell. And these electrons must be removed sequentially. So we remove the first electron, and the energy required to remove electrons is the one that we refer to as the ionization energy. And we are removing electrons from gaseous atoms. So that is the first ionization energy of calcium. And when you ionize, you form positively charged ions, thus, and you release the electron plus your half O2, not yet atomized. And then the next process, and I then also atomize there. I now remove the second electron because calcium is in group 2, so it has 2 electrons in the outer shell. So this is now the second atomization, whereby you remove one mole of electrons from the calcium, positively charged calcium ions. This is the second ionization energy. Now I have 2 moles of electrons, and here I'm atomizing the oxygen. So when you atomize, you now get the oxygen atoms. Now we have generated the electrons. Oxygen is an atom. It still requires 2 electrons, so it's now going to gain the electrons. And the gain of electrons to form negatively charged ions is referred to as electron affinity. So this is the delta H electron affinity for oxygen. This is the first electron affinity, whereby it gains 1 electron to form O2 minus. Still there is another electron, and this process is an exothermic process because it's an atom combining with an electron, so there is attraction. But the second electron affinity is endothermic, because you are adding a negatively charged electron to a negatively charged oxide ion. So there's going to be repulsion. So energy is required. Hence, there is an increase in energy. It's an endothermic process, so that you form. So don't forget to put the state symbols. You now form that plus O2 minus X. We have now formed the gaseous ions. In these gaseous ions, when they now combine, you now form the ionic solid, and this is the delta H lattice energy for calcium oxide. So this is the Born-Haber cycle. So we now want to use this Born-Haber cycle that we have constructed to calculate the lattice energy for the formation of calcium oxide. We are going to use the Born-Haber cycle to calculate the lattice energy. We are also given the atomization energy of calcium as plus 178 kilojoules per mole. And we are also given the enthalpy change of formation as minus 635 kilojoules. And we are also given the electron affinity, the first and second electron affinities of oxygen. They are already combined, and there is plus 657 kilojoules per mole. That is what we are given. So, together with information from the data booklet, we should now be able to calculate the lattice energy. So what we are now saying here is, according to Hess law, if we form calcium oxide following this route, from here we go all the way to here. This is route 1, that is the same as this one. So basically we are simply saying delta H formation of calcium oxide, the energy, that energy is the same as adding delta H atomization of calcium plus delta H first ionization plus delta H second ionization plus delta H atomization plus delta H electron affinity 1 and 2 plus lattice energy. When we take all these processes, the energy change involved should be the same as delta H. This is going one way, that is the other. So the total energy change should remain the same. So in our computation, we don't have the first ionization energy, the second ionization energy, and we don't have delta H atomization of oxygen. And we are going to use our data booklet to determine that. So you take the data booklet, and for ionization energy, you go under ionization energy. And here we need the first and second. So the first and second ionization from our data booklet for calcium is 590 and 1150. And then atomization of oxygen for all diatomics. For all diatomics, please note, their atomization energy is the same as simply breaking the covalent bond between the two atoms. So in oxygen it's a double bond, so you go to the O double bond O bond energy. So you use bond energy data, and here you get, since we are using only one, so this is half times 496. That's the bond energy. And that is the same as the atomization energy. When you supply that amount of energy, you break the oxygen bond energy. But this time we only need one more of oxygen, here we take the half. So we now take the values. So we are simply saying minus 635 is now going to be equals to plus 178 plus 590 plus 1150 plus half of that is 248 plus 657 plus lattice energy. We don't know that one. So before you change and make L the subject of the formula, I would advise you to first evaluate this. And when you evaluate and then you make L the subject of the formula. And when you do that, you must get lattice energy is minus 3458. So our lattice energy is going to be minus 3458 kilojoules per mole. That is the energy which is released when one mole of calcium oxide is formed from its ions. And that same amount of energy which is released when it is formed, basically is also the same amount of energy which will be required when you want to break the lattice. Okay, so that was the part. The next part, explain how and why the lattice energy of calcium oxide is different from that of strontium oxide. When you look at the periodic table, calcium and strontium, they are both elements in the group 2. But as you go down the group, the atomic radii is increasing because of the increasing number of atomic shells. So strontium is lower than calcium, which means strontium has a larger atomic radii. And because of the larger atomic radii, the ionic bonding in strontium is much weaker than that in calcium. Hence, this is the reason why the lattice energy of calcium oxide is going to be greater than that of strontium oxide, because the strontium ion has a larger atomic radii, is a larger ionic radii compared to the calcium ion. Hence, when the strontium ion and the oxide ion approach each other, the ionic bond length is going to be longer. Okay, so in this case we say strontium ion is a lower charge density. It is a lower charge density because the charge is still the same, it's +2, but it now has a larger ionic radii. That is the reason why calcium oxide is going to have a more exothermic lattice energy compared to that of strontium oxide. Then the last part, the C part. An ice pack is used as a simple treatment for minor strains and sprains. It consists of a thick plastic bag containing ammonium nitrate powder and a second thinner plastic bag full of water. If the bag is given a sharp blow, the thinner bag bursts and the ammonium nitrate dissolves endothermically. The drop in temperature depends on the mass of the ammonium nitrate used and the volume of water which is also used. And here we are given that the enthalpy change of solution of ammonium nitrate is plus 26 kilojoules per mole, and the specific heat capacity of the resultant solution is plus 4.2 joules per gram per Kelvin. Calculate the mass of ammonium nitrate. That would decrease the temperature of 500 cubic centimeters of water by 25 degrees C. So we are given the enthalpy change of solution. Enthalpy change of solution is basically the heat change which is given out or absorbed. So the enthalpy change when 1 mole of the ammonium ion dissolves in a large amount of water, such that further dissolution does not result in any further heat change. That is enthalpy change of solution. So for us to find the heat change, we use the formula is equals to MC delta T or VC delta T, where M is the mass of our ammonium nitrate. Here we use the relationship 1 gram is equals to 1 cubic centimeter or volume. So if I have the volume, and in this case we are using the volume of water because this is where the dissolution is going to occur. So this is the volume of water, this is the specific heat capacity, and this is the temperature change which must be affected by the reaction. So our total mass, the volume of water, is 500 times. We don't need the mass of the solid. Why? Because the solid particles are going to be dispersed in between the water particles. Hence, they do not result in any change in the total volume. Times 4.2 times 25, because we need to effect a 25-degree drop in temperature. And when we calculate this, the heat change, total heat change is equals to 52,500 joules. But let's remember, we are told that 26,000 joules will deposit will dissolve 1 mole of ammonia. Therefore, how many moles of the ammonium nitrate are being dissolved by this amount of heat? So we divide this by 26,000. We're given as kilojoules, we multiply by 1,000 to convert into joules. And when we do this, we can see that this amount of heat is released when 2 moles of ammonium nitrate dissolve. So 2 moles of ammonium nitrate must dissolve in order for me to release this amount of heat energy, or for there to be a drop in temperature of this magnitude. Since the reaction is thermic. Okay, that is the energy which will result in the 25-degree change, and that is due to 2 moles. So let's find the mixture for ammonium nitrate so that at the end we can now determine the mass. So nitrogen with 2 moles of nitrogen, 14 plus 4 moles of hydrogen plus 1 plus 3 moles of oxygen, and this should give me a total of 80. That is the mass for 1 mole. But in this reaction I'm using 2 moles, hence the mass. Hence the mass of ammonium nitrate required is 80 times 2. And this is equal to 160 grams. So if you dissolve 160 grams of ammonium nitrate in 500 cubic centimeters of water, we expect a decrease in temperature of 25 degrees Celsius. Basically, that is what this statement is saying. Please subscribe, like, and share. I'll see you in the next section.